Hello everyone. Title of this video is Solve Applications with Proportions. So whenever you see the word applications, that should indicate to you that we're going to see word problems. Now these are going to be very short word problems in which we set up a proportion, which is an equation where you have a ratio equal to a ratio or a fraction equal to a fraction, and then solve. Alright, so every exercise I'm doing in this video is taken directly from a free online textbook at openstax.org. This is their Intermediate Algebra 2nd edition textbook. I'm in section 7.5, titled Solve Applications with Rational Equations. And I'll be working on exercises 263 all the way through to 274. That's 12 examples. And so example 1 in the video will correspond to 263. Example 2 will be 264, and so on until example 12 will be exercise number 274. And I will have timestamps for each of the examples in the description of the video if you want to bounce around and look at any particular problem. Alright, you just have to count, which example you want to look at. You have to count down what example that would be. And one thing else I request of you is that when I bring up a new example, pause the video and try to do it yourself first before watching me do it. Because if you're just watching me do it and not practicing yourself, probably not going to be learning much of anything. Alright, so let's get started here. I'm going to pull up a piece of paper along with this. Now it's going to look a little tinier now, but on occasion I'll bounce back and forth, make it bigger. You see the work, right? You see my cursor moving around the website in the upper left corner, and I got my paper out here in the lower right corner. So number 263, example 1. So it says here, Kevin wants to keep his heart rate at 160 beats per minute. Now when you see the word per, P-E-R, that usually implies a ratio, a fraction, a rate. And you've seen per before, right? Miles per gallon in a vehicle. Dollars per gallon for gas at a gas station. Dollars per dozen for donuts at a store. Miles per hour for speed. All these are ratios. Can be written as fractions. And there are units involved, right? The heart rate units are beats, and you'll have these time units of minutes. Alright, so once again, Kevin wants to keep his heart rate at 160 beats per minute while training. During his workout, he counts 27 beats in 10 seconds. So part A is how many beats per minute is this? Alright, so we have to do some unit conversion. So I set up a ratio. They want beats per minute. We have this ratio, they say Kevin counted 27 beats, right? So I got beats in the numerator. Per, right? Per implies division, implies a ratio, a rate. Per 10 seconds. He had 27 beats per 10 seconds. In 10 seconds. So I've got my heart rate units in the numerator, time units in the denominator. Alright, so I'm going to make this a little bigger now. Let's bring this back up. Okay. Now they want beats per minute, not beats per seconds. So right now, if I divide these, 27 divided by 10, that's 2.7 beats per second. right now, right? But I don't want beats per second. I want beats per minute. So we're going to do some unit conversion. So I'm going to multiply here by a conversion factor. I'm going to multiply by another fraction where the numerator and denominator have the same value. That way it'll be like I'm multiplying by 1, and the expression's value will not change. So I would like seconds to cancel. So I'm going to put, seconds is in the denominator of this fraction. So I'm going to multiply by seconds, in the numerator here. And then I want to change it to beats per minute. So I want minutes in the denominator. And then what's an equivalency between minutes and seconds? Well, 1 minute is 60 seconds. All right, so you see the seconds canceling. And then I can even do some cancellation as well with, 10 goes into 60 6 times. So the common factor of 10 in the numerator and denominator cancel. And now I'm left with 27 times 6. I'm left with 27 times 6 in the numerator. Now that'd be 120 plus 42. That'd be 162. And then the units in the numerator is still beats, heartbeats, right? Per, and then I've got when things cancel. When an entire factor cancels, you still have 1. You have 1 times 1 in the denominator. That's 1. And the units left over in the denominator is minutes. So counting 27 beats in 10 seconds is equivalent to 162 beats in 1 minute. And then dividing these, now 162 divided by 1 is simple. That's just 162. And we have beats per minute, beats over minutes. Or BPM, right? You might see that abbreviated as BPM, right? Beats per minute. But this is what they wanted for part A. Right, so part A was simply do the conversion, right? How many beats per minute is this 27 beats in 10 seconds? Then part B, has Kevin met his target heart rate? Well, yeah, his target heart rate was 160 beats per minute. So part B, yes. The answer is yes. Kevin met his target heart rate, right, of 160 BPM. I'll just put beats per minute, because again, that 162 is more than this. He beat it. He met it. Right. So I'll later on I'll just put the word yes or no, if we're answering a yes or no question. But usually with application problems, word problems, right, it's proper to write your answers in complete sentences. Great. All right. So this one really didn't involve any proportions. This was just a practice in unit conversion. I'm sure that exercises coming up, and I'm looking ahead here. There will be exercises coming up where we set up a proportion, right, where we have a fraction equal to another fraction. Now, I guess you could call this a proportion, because I have a fraction here equals a fraction there, but we'll be setting up proportions later where one of the numerators or denominators is unknown and we have to solve for it, right? I didn't really have to solve for anything here. I was just doing unit conversion. All right, so let's look at example 2, which is exercise 264. All right, so Jesse's car gets 30 miles per gallon. All right, again, there's the per again, a rate, a ratio, a fraction, 30 miles over 1 gallon of gas. A, if Las Vegas is 285 miles away, how many gallons of gas are needed to get there and then home? there, and then home. All right. So let me set up a proportion. So again, I'm gonna pull this up so the paper and the problem are on the same screen here. So example 2. Now, a proportion. This is one where we're actually going to set up a proportion. Now, I've brought up proportions before in a previous video related to section 7.5 here in this text. It's just a ratio, so A over B equal to another ratio, another fraction, C over D. Now, the key to setting up a proper proportion is the units you're using. If I set two ratios equivalent to one another, or two rates, the numerator units should be the same. What I mean by that is, if I have miles in the first numerator on the left fraction, I should have miles as the units on the right fraction. If I have gallons as the numerator units of the left, I should have gallons as the numerator units on the right. So make sure your units are consistent. Same thing for the denominators. When I set up a proper proportion, ratio equals ratio, rate equals rate, the numerator units should be consistent, and the denominator units should also be consistent. So keep that in mind. So here, the left ratio, where we were given a rate of Jesse's car's gas mileage. Jesse's car gets 30 miles per 1 gallon, or 1 gallons if you want. So this is Jesse's car's gas mileage here, and it should stay the same no matter what kind of trip Jesse's taking in this car. So this ratio should be equal to the following. And I'm setting up another ratio on the other side where the numerator's in miles. Now, remember they said there and back, right? The question is how many gallons of gas are needed to get there and home, right? And Vegas is 285 miles away from wherever Jesse is. So we're doing this twice. I hope this makes sense, right? It's 285 miles there, and then 285 miles back. So that'd be 570 miles. So I'm putting that in the numerator of this ratio on the other side, right? And once again, this is distance to Vegas and back. Vegas and back home. Right? They wanted both. So miles are both in the numerators, and then the question was how many gallons of gas, right? The number of gallons is unknown, and that's in my denominator here. And since it's unknown, and like with any word problem, when something's unknown, we can call it a variable. I'm just going to put X for unknown gallons of gas are needed to travel these 570 miles. And since we're traveling in Jesse's car, both these ratios should be the same. Right? Jesse's car gets 30 miles for 1 gallon, So Jesse's car should get 570 miles for how many gallons of gas, right? And these ratios should be the same because we're using the same car. And then I'm solving this. So again, I'll make this bigger. And then so this is a proportion, and then we solve the proportion, right? Solve the proportion. Now you don't need, since my units are consistent, right? Numerator units are the same, denominator units are the same. I'm just going to write it without the units. So we have 30 on the left, right? 30 over 1, but there's no reason to write over 1, equals, 570 over x on the right. And then you solve this proportion like I've solved proportions in a previous video, or solved any rational equation, any equation with fractions. All right, first I find the LCD. Now, I hope it's obvious that the LCD, right, the least common denominator here is just x. I multiply both sides by x, and that'll cancel the denominators, right? The only denominator here, x, gets canceled on this right side. So on the left side I have, 30 times x equals, and then the right side, right, the x's cancel, and I have 570. And then I'm dividing by 30, right? So x equals 19, right? 3 times 19 is 57. 30 times 19 would be 570. Now this isn't the answer, right? This helps me answer the question, right? This is the solution of that equation. You got to remember what it means though, right? And as I said before in example 1, usually you answer questions in complete sentences, right? So x is 19. That means that Jesse's car needs, let's say Jesse's car would need, or needs 19 gallons, right? X represents the number of gallons here. Needs 19 gallons of gas to make it to Vegas and then back home, right? For it to be able to make it to Vegas and back. And then back home, or just Vegas and back. And this is how I would answer this question, with a nice complete sentence that makes sense in the context of the problem. All right, now this was, part A of the question. Right? Need 19 gallons to make it there and back. And then part B, for, again, the exercise 264 here, if gas is $3.09 per gallon, what is the total cost of gas for the trip? Right. So I'll just bring up this again, right? And I'll say it out loud what they said to us. Right? So again, we have a ratio. The cost of gas is $3.09. So $3.09, right? The units up here are dollars per 1 gallon. Right, or 1 gallons if you want to. But there's a rate, a ratio. And since again now I know this doesn't make sense in real life, because gas might change from if because most vehicles don't hold up to 19 gallons, so you're filling up and then you're probably going to run out of gas and then fill up again at a different gas station and have a different price. But don't worry about any of that, right? Let's just assume that gas costs $3.09 per gallon, and this should be equal to the ratio of the gas per gallon that we spent on this trip. Now the total cost is unknown. So again, now since I used X already, I'm going to use C for cost. Cost C dollars. I don't know the cost for the trip, but I do know how many gallons of gas would be used for this trip. That'd be 19 gallons. So I'm setting up another proportion over here. Costs $3.09 per gallon. And then we're spending how much money? I don't know, for the 19 gallons. And we're solving this proportion. I got 3.09, divided by 1, but again, no need to write divided by 1, equals C divided by 19. And then I would just simply multiply by 19 here. All right, so C, the cost of the trip, would be whatever 19 times 3.09 is. And I'll just punch that in a calculator. 19 times 3.09 is $58. Right, so this is 58.71. And you got to remember what that means, right? Yes, this is the solution of this equation here. But then write out what this means, right? The trip, the cost of gas for this trip is $58.71. You got to put units on it to have it make sense. All right. So setting up proportions, ratio equal ratio, and again, once again, make sure your units are consistent, right? Numerator units here were both dollars. Denominator units were both gallons. The numerator units should be the same in your proportion. The denominator units should be the same, right, to make a proper proportion. All right, next example. Exercise 265. So it says here, pediatricians prescribe 5 milliliters, or ml, right, of acetaminophen, Tylenol, right, for every 25 pounds of a child's weight. All right, now for every is just like per. 5 milliliters per every 25 pounds. Cancel this, sorry. Get out of there. All right. 5 milliliters per 25 pounds of a child's weight. Stop highlighting stuff. Sorry about this. All right. Then the question is, how many milliliters of acetaminophen will the doctor prescribe for Jocelyn, who weighs 45 pounds? So once again, I have a ratio, milliliters to pounds, given initially, and I have another ratio, question mark milliliters to pounds. We can set up this proportion. Right. So again, I'll keep the problem up. Right, you can see number 265. Right. And this is example 3. So the left ratio is, it said they prescribed 5 milliliters of acetaminophen, so 5 ml per, or for every 25 pounds, which is usually lbs, right, lbs. They prescribe 5 milliliters of acetaminophen per, or for every 25 pounds of a child's weight. And this ratio should stick, right? This should be equal to the ratio of milliliters prescribed to Jocelyn per her weight. How many milliliters? The question is, how many milliliters of acetaminophen are prescribed? I don't know this. So again, I'm going to call this X milliliters. So this doctor prescribes how many milliliters, X milliliters, for the child's weight, and this child, Jocelyn, weighs 45 pounds. All right. So I'll make this a little bigger. All right. So here's my proportion. So again, you got the ratio prescription to weight for every child, and then here's the ratio for Jocelyn. Right. And they should be the same, because Jocelyn is also a child. And this is solving this proportion. We have, now that my numerator units are the same, my denominator units are the same, so I'm going to ignore those for now. Right, I've set up a proper proportion. So I have 5/25 on the left equals X over 45 on the right, and I'm solving for X. now you've seen me do this before as well. If there's, I would prefer to simplify the fractions first if I can and then solve the proportion. 5/25, that reduces to 1/5. So I have 1/5 on the left equals, x over 45 on the right. And then the LCD would just be 45. I would just multiply both sides by 45. And then, 5 goes into 45 9 times. You'd be left with 9 times 1, or 9 on the left. And 45's cancel. You have x on the right, and there you go. But I have to make it make sense, right? X equals 9 is just the solution of the proportion. Remember what x represents. X represents the number of milliliters of acetaminophen prescribed to Jocelyn. Right, so the doctor would prescribe 9 milliliters of acetaminophen. Am I spelling that right? To Jocelyn. All right, make it make sense for the problem at hand. All right, but same thing, setting up a proper proportion. You have the numerator units are consistent, the denominator units are consistent. Okay, next question. So we're looking at exercise 266. A veterinarian prescribes Sunny, a 65-pound dog, an antibacterial medicine in case an infection emerges after her teeth were cleaned. If the dosage is 5 milligrams, right, mg, for every pound, how much medicine was Sunny given? So this is a pretty similar setup. All right, so once again, I'll pull this up. We're looking at now, this is example 4, exercise 266. Same setup pretty much. They told us the dosage was 5 milligrams of drug per every pound. So I got milligrams in the numerator, pounds in the denominator. 5 milligrams of the drug is prescribed for every, or per pound, 1 pound of dog. This ratio should stay the same for this dog, right, Sunny. So over here, the question is, how much antibacterial medicine was given to Sunny? How many milligrams? So again, I don't know this, so I'll call it X again. Now you can call it whatever you want, right? But X milligrams of this drug were given to Sunny for, and Sunny's weight. Sunny weighs 65 pounds. And I have my proportion set up, and it is a proper proportion. All right, numerator units are consistent, denominator units are consistent. And so I'm solving this. The left side is just 5, all right, 5 over 1. The right side is x divided by 65. And I would just be simply multiplying by 65. All right, 5 times 65 would be 325. There's the solution of the proportion. Again, make it make sense for the problem. Remember what this represents. It represents the number of milligrams of this antibacterial medicine that was prescribed to Sunny. So I'll just say Sunny, the dog, was given 325 milligrams, right, there should be units involved to give numbers meaning, of the drug. I'll just say of the drug, of the medicine. Right. And there you go, that's how I would answer this question. Okay. All right, next question. So example 5, this is going to be exercise 267. So a new energy drink advertises 106 calories for 8 ounces, right, for every 8 ounces. So I'm going to have this ratio, 106 calories per, or divided by 8 ounces. And then how many calories are in 12 ounces of this same drink? Alright, so I'm going to just write it on paper now and read it out loud again. Hopefully you see it here. But so this is example 5. We'll come back to paper here. Now, again, the ratio they gave us, they said this energy drink had 106 calories for every 8 ounces, right, usually abbreviated OZ. And this should be equal to, the ratio for any amount of energy drink drunk. Okay. So the question is, how many calories? So again, calories will be in the numerator. I don't know the number of calories. So X calories are there in 12 ounces of the drink. And ounces in the denominator. So we're solving, again, numerator units same, denominator units the same. This is a proper proportion. So we have 106 over 8, which I can simplify. I will simplify that on the left, equals, and then x over 12 on the right. Now this is just 53 over 4 on the left, right? 53, 2 times 53 in the numerator, and denominator is 2 times 4. 2's will cancel. Alright, and that's as much as that reduces. And then we have x divided by 12 on the right. And the LCD would just be 12, right? So I would just simply be multiplying by 12 here. And multiplying by 12 on both sides. The 12's cancel on the right side, leaving me with x. And then 4 goes into 12 3 times. So I'd end up with 3 times 53 on the left side. So we have x equals, I'm just switching sides now, x equals 3 times 53 would be 159. So again, that's just the solution of the proportion. Have it make sense though. What did x represent? That represented the number of calories in a 12-ounce drink. So I'll write out there are 159 calories in a 12-ounce drink. Great. A complete sentence to give it meaning. Okay, moving on. Example 6. Alright, that would be exercise 268. And it looks pretty similar to 267. One 12-ounce can of soda has 150 calories. So there's, ounces per calories, or calories per ounce if you want to do it the other way around. If Josiah drinks the big 32-ounce size from the local mini-mart, how many calories did he drink, or does he get? So again, I'll just pull up a new sheet of paper here. This is example 6, exercise 268. So the first ratio, and I'll do calories per ounce. Just make sure again that your units are consistent in the numerators and denominators. So this soda, there are 150 calories in a 12-ounce can. Right, so 150 divided by 12 there. Right. And this should be equal to the ratio for Josiah's drink. The question is, how many calories did he get? So again, I don't know the number of calories. Call that x. So there are x calories in the 32-ounce drink that Josiah is drinking. So again, just make sure you're set. Now you can flip these if you want, but again, just so long as you're setting it up so that the units are consistent. Now, so I'm solving this proportion, right? 150 over 12 equals x over 32. this is 6 times 25, this is 6 times 2, so this reduces to 25 halves. 25 halves equals x over 32, and then multiply both sides by 32. Right. And the 32's cancel over here. 2 goes into 32 16 times, and 16 times 25 is 400. Right, every 4 would be 100. 16 is 4 times 4. So x equals 400. Alright, so that means there are Josiah drinks 400 calories of soda. Right. Again, x represented the number of calories in Josiah's drink. Okay. Next example is example 7. This will be exercise 269. So we have Kira is traveling to Canada and will change 250 US dollars into Canadian dollars. At the current exchange rate, 1 US dollar is equal to 1.3 Canadian. So how many Canadian dollars will she get for her trip? All right, so same deal. I'm given 2 units here, US dollars and Canadian dollars, right? Those are different units, right? I know they both say dollars, but they are different units, right? US dollars and Canadian dollars, right? So again, I'm going to pull up some paper here. This is example 7. So the one ratio they gave us is that 1 US dollar, I'll put USD, is equivalent to every US dollar. There's 1 US dollar for every 1.3 Canadian dollars. And I don't think this is the actual abbreviation for Canadian dollars, but CD. Right. So US dollars, for 1 US dollar for every 1.3 Canadian dollars, or you could flip it around and say there's 1.3 Canadian dollars for every US dollar. That's the exchange rate. Right, and this should be equal to the ratio for the exchange rate, the exchange rate that she's using with the money she has. And she's changing 250 US dollars, right? They said she had 250 US dollars, and it's changing it to Canadian dollars. And the question is, how many Canadian dollars will she get? So again, I don't know this. We'll call this X Canadian dollars. Again, CD is for Canadian dollars. So I've got 1 over 1.3 equals 250 over X, which I think it'd be easier to flip this. Right? We could flip it and say there's 1.3 equals X over 250. Right? So all I did was reciprocals. I just flipped both sides. Right, instead of having US dollars in the numerators, I have Canadian dollars in the numerators now. And that would just simply multiply by 250. Right, equals 1.3 times 250. Alright, so X equals, now 13 times 25 would be 325. So this is 325. Now remember, you got to have this, you got to give this meaning. Right, 325 what? That's, remember what X represented was Canadian dollars. That, what was her name? Kira will get. So Kira, if she exchanges 250 US dollars for Canadian dollars at this rate, Kira will get 325 Canadian dollars. dollars Canadian for the trip. I don't know why I needed an exclamation point there, but a period would have been fine. But yeah, again, make it make sense, right? It's got to make sense for the problem. All right. So again, pretty much all these are the same thing, right? You're setting up a proportion, just make sure your units are consistent and solving that proportion and answering the question. All right. Now example 8, this will be exercise 270. So we got Maurice is traveling to Mexico and needs to exchange $450 into Mexican pesos. Right? So you have American, dollars and pesos, Mexican pesos. If each dollar is worth 12.29 pesos, how many pesos will he get for his trip? So pretty similar to the Canadian dollar problem. All right, so again, this is example 8. So the exchange rate they gave us was, there were 12.29 pesos, right? 12.29 pesos for every American dollar. Each dollar, $1. Right, let's put the US. You can put American dollar, USD, or just the dollar sign there. And this exchange rate should be equivalent to the rate he gets for his money. Now the question is, how many pesos will he get for the trip? So the number of pesos is unknown. So again, I'll call that X. And for the money he exchanged, it was $450. He exchanged $450 US dollars for pesos. Again, I got dollars, US dollars in the denominator, pesos in the numerator. And we're really just, now that the units are consistent, we're just solving this equation, 12.29, divided by 1, 12.29 on the left, equals just X over 450. And all I'd be doing is multiplying by 450. So I'm just going to use a calculator off to the side here. We got 12.29 times 450. So this is 5,530.5, or 0.50. Usually money goes to 2 decimal places. So this is how much money Maurice would get in pesos. Right. So I'll write that. Maurice will get 5,530.50 pesos, Mexican pesos, for the trip when exchanging that $450. Okay, and again, you should be, for any word problem, writing a complete sentence to have the thing make sense at the end. All right. So next question, example 9, is exercise 271. So it says there, Ronald needs a morning breakfast drink that will give him at least 390 calories. Orange juice has 130 calories in 1 cup. So how many cups does he need to drink to reach his calorie goal? So the units here are, calories and cups. And again, I'm going to set up a proportion. So this is example 9. So they're talking about they tell us that orange juice has 130 calories in every cup, per 1 cup. And this ratio should be equal to the ratio he drinks, for the calorie, the daily calorie count he wants. Say he wants 390 calories. Say Ronald wants to drink 390 calories of orange juice. And the question is, how many cups? So X cups. So I got cups in the denominator, calories in the numerator. So we're solving this equation here. 130 equals, 390 divided by x. Now you could flip it if you want, but I'll do this. I'll multiply by x. The LCD is just x here. 130x equals 390. And then dividing by 130, I hope it's obvious that x equals 3. 39 divided by 13 is 3. So Ronald needs to drink 3 cups to reach his calorie goal. And really, you should say he needs to drink at least 3 cups, right? Because his calorie goal was at least 390 calories. So 3 cups or more. But I'll just say Ronald needs to drink 3 cups of orange juice, of OJ, to reach calorie goal. Great. And again, make it make sense. All right. Next question. All right. See, very similar setup to all these. You just got to pay attention to the units that are brought up. All right, so example 10 will be exercise 272. Sonia drinks a 32-ounce energy drink containing 80 calories per 12 ounces. How many calories did she drink? All right, so this is pretty similar to an earlier question. So once again, new piece of paper here. This is example 10. Setting up a proportion, ratio equals ratio. So they tell you that there are 80 calories for every 12 ounces of this drink. Right, so 80 calories per 12 ounces. And this ratio should be equal to the ratio of the drink that she drinks, Sonia drinks. So the question is how many calories, right? We don't know the number of calories. So again, I'm going to say X calories. There are X calories in the 32 ounces that she drank. So once again, the units are consistent. Calories in the numerator, ounces in the denominator. And I'm solving this, right? This proportion, 80 over 12 equals X over 32. And then like a lot of the other problems, right? 80 over 12 can reduce. All right, this is 4 times 20. This is 4 times 3. 4s would cancel. This is 20 thirds when you totally reduce it. All right, 20 thirds equals, and then X over 32. All right. And then we would just simply multiply by 32. Oh, not really. Oh yeah, to get X alone, you'd multiply by 32. But now 32 isn't the LCD. All right, the LCD would actually be 96. So if I were to do that, if I multiply both sides by 96, say 3 goes into 96 32 times, 32 goes into 96 3 times, you'd have 3x on one side equals 640 on the other, and then dividing by 3, you'd have 640 divided by 3. That does not reduce anymore. Right? 3 doesn't go into 640 evenly. It would go into 639 evenly. Right? Be 213 and 1/3. Right? If you wrote it as a mixed number, calories. Right? Or 213.33333333. Right? Yeah. But yeah, so Sonia drank 213 and 1/3 calories. Or you could write 640 over 3, calories. That's totally fine as well. All right. Okay. And then next question, example 11, which will be exercise 273. Phil wants to fertilize his lawn. Each bag of fertilizer covers about 4,000 square feet of lawn. So you have bags of fertilizer, so bags, and then square feet of lawn, or square feet, right? The units that are represented here. Phil's lawn is approximately 13,500 square feet. How many bags of fertilizer will he have to buy? All right. So again, back to this question. This is example 11. All right, so they gave us this ratio, this rate. For the fertilizer covers 4,000 square feet. I'll put square foot, SQFT. Each the fertilizer covers 4,000 square feet per bag. Right. So, one bag, 4,000 square feet per one bag. There's that ratio. And that should be equal to the amount of the ratio Phil uses for his lawn. Now Phil's lawn, they said, is approximately 13,500 square feet. And so I'm putting that in the numerator of this ratio, because again, the numerator units should be consistent. And the question is how many bags of fertilizer, right? That's the unknown, so divided by X bags. So I have 4,000 on the left equals 13,500 divided by X on the right. I would multiply by X, I get 4,000X equals 13,500, and then divide by 4,000. So now 2 of the zeros would cancel, so basically it would be 135 over 40, but that reduces even further. 5 goes into that 27 times, 5 goes into this 8 times. So this reduces to 27/8. Now 8 doesn't go into 27 evenly, but it does go into 3 times. 3 times 8 is 24. So this is 3 with 3/8 left over, 3 and 3/8. Now this doesn't make any sense. Right, again, you got to have it make sense to the real world, right? You can't buy, right? You can't go to a store and buy 3/8 of a bag of fertilizer, right? You can't just open up a bag of fertilizer and take 3/8 of it out and then say, I'm only paying for this. So 3 bags would be too little, right? He needs 3 and, 3, this is, 3.375 bags. If you put a decimal, 3/8 is 0.375. 3 bags would be too little. So in order to be able to cover his lawn, Phil has to buy 4 bags. So to make this make sense, Phil has to buy, again, you could write 3 and 3/8, that wouldn't be wrong, but in real life, right, like I said, you can't just buy 3/8 of a bag of fertilizer. Phil would have to buy 4 bags of fertilizer to be able to cover his lawn in fertilizer. Fertilizer. Right. Again, entering 3 and 3/8 wouldn't be wrong. It just wouldn't make sense in real life. I'm trying to have things make as much sense as possible in the context of the problem. I hope that makes sense. All right. Final question. Final example. All right, this is exercise 274. All right. So an oatmeal cookie recipe calls for half a cup of butter to make 4 dozen cookies. So cups of butter to dozens of cookies, right? These are the units here. Hilda needs to make 10 dozen cookies for the bake sale. How many cups of butter will she need? So again, a proportion, right? Ratio equals ratio. Example 12. So the ratio we were first given is that it takes half a cup of butter. So half cup of butter, half cups of butter to make, for every 4 dozen cookies. Dozens of cookies. Now I guess I could just say cups and dozens. But my numerator units are cups of butter. The denominator units are dozens of cookies. And do you see what I have here? It's actually a complex fraction. We'll simplify that in a second. Equals. And then again, the ratio for the recipe should be the same as the ratio used by Hilda. She's making 10 dozens of cookies, right? 10 dozen cookies, and dozens of cookies is in the denominator here. Right? So I got 10 dozens of cookies she's making. And the question is how many cups of butter will be needed. So that's X cups of butter. All right, so your numerator units, denominator units are consistent. So we have 1/2 over 4. Right? There's a complex fraction, which I'll simplify in a second. And over on the other side, we just have X over 10. Now remember a quick way to simplify a complex fraction is to multiply the numerator, which is 1/2, and the denominator by the LCD. The only denominator showing up within the fraction is 2. So if I multiply the numerator by 2 and the denominator by 2, that should cancel that, right? 2 times 1/2 is just 1, and 2 times 4 is 8. All right, so 1/2 divided by 4 is 1/8. All right. Equals X over 10, and then I would just be multiplying by 10. So X equals 10/8. 10 times 1 over 8, 10/8, which would reduce to 5/4. Or 1 1/4 if you like mixed numbers, or 1.25 if you like decimals. These are all the same number. So this is telling me that Hilda would need 1 1/4 cups of butter, right? 1 1/4 cups of butter for these 10 dozen cookies. And this does make sense, right? You can have a 1/4 cup, right? It wasn't like the bag of fertilizer problem, right? From example 11. Okay, great. So yeah, so that's it. All 12 examples, right? Exercise, 263 through 274. Every single one was pretty similar, right? You set up your ratios and made sure your units were consistent, right? Numerator units were the same and the denominator units were the same. And then you could, ignore the units for a second, solve the proportion, and then, answer the question. Write a complete sentence, make it make sense. All right, so I'm hoping that watching me go through these 12 examples, setting up proportions to solve problems, helps you when you're working on similar questions. And thank you very much for watching.